ahead and start for today. One of the first things that I would like to do before we get going is I would like you to get together with about the 4 or 5 people that are surrounding you. I'd like somebody to get out a piece of notebook paper. And so if you can move to get together with 4 or 5 people around you, then I will explain to you what we're going to do. Somebody needs to have a piece of notebook paper. Since you guys are right here, could I have you move one of these chairs over here so that you guys can work with her? Will you get with her, and then 1 or 2 other people, or at least trying to get some people working together. You know what? Why don't you move over with them? Ladies, can I have you work with her right here, please? Thank you very much. Okay, guys, so here's what I want you to record every person's name on the paper so that I know who it is that you're working with. And I would like you to write down some of the things that you liked about doing your assignment online on Thursday, or some of the things that you did not like. I know there's going to be strong opinions about it, but I need to get some feedback from you as to things you like, things you don't like, and this is a chance to voice your opinion so that I know what it is that you're doing. Also, if there's anything you want to suggest to me that you would like to see happen in this class, now is your time to give me some feedback about what you really think. So go ahead, and I would like for you to take about 3 minutes, 3 to 5 minutes to write down your opinion on how things are going so far. I'd like every person in here to make sure they make at least some contribution to the conversation. Write down something that at least everybody thinks about the Thursday assignment or about the course as a whole. Okay, guys, so as you're taking the last couple of minutes to finish up writing whatever your critique was of the assignment, I want you to write down one thing. I want each of you to put one thing that you would like to get out of this course, one thing you'd like to learn, if there's any burning topic of biological knowledge that you have about life or things living on Earth, one thing that you would really like to know about, and I'll attempt to hit it this semester. There's got to be something you're interested in. All right, take about 1 minute to finish up, and then we're going to move on with our notes. Whenever you're finished, go ahead and send the papers to the outside of the rows, and I'll come by and pick them up. And if you want to start moving back to wherever you're comfortable, I'll start up here in another 30 seconds. So if you can just set the papers on the outside rows, then I can come around and pick them up. Whichever side, I'll make a circle. Whichever is closer for you. Okay, guys, so as we're finishing up here, I wanted to let you know I've started going through and started to grade the Thursday assignments. For the most part, if you got it turned in, as long as you put in something about each one of the video, you're going to get each one of the points. So I also put in some suggestions for certain people about all those little squiggly lines mean spell check, and writing in not complete sentences, but understandable sentences is always helpful. And I haven't made it through all of them yet, but I will attempt to make it through those as soon as possible. So if you missed one of them, if you didn't manage to get it in, or you had some kind of problem with that assignment, then missing one is not going to affect your grade at all. We'll just make sure to get this accomplished going forward from here. So as we are continuing on today, we're going to finish up with talking about Chapter 1, if this is going to work. In finishing up what we were talking about in Chapter 1, we've been talking a little bit about the scientific method, how science works, what do scientists do, what are we going to be doing as far as this class goes, talking about a little bit about DNA and genetics, talking about chromosomes, we'll be talking about ecology and the environment, and we'll be talking about how things change over time. One of the ways that scientists can best understand what's going on in the world around us is through statistics. And usually when we think about statistics, sometimes they are overwhelming because we're not sure how all the formulas work, we're not sure how people got to their understandings. But statistics is really a great tool because it can help us in our decision-making process. Basically, what statistics is a set of analytical and mathematical tools designed to help researchers gain understanding from the data that they gather. So if we're counting the number of times that a cricket is chirping, if we're counting the number of times something is happening out in the environment, if we are capturing to what magnitude it happens, any way that we can go about collecting numbers about something and then going through an analysis, a factor analysis, using computers to make graphs and things like that. Statistics is really just a mathematical tool to make sure that we can further understand what do those numbers mean, because that's really what we're looking for. We're trying to find trends or patterns, or being able to graph things over time, or graph things at certain temperatures, or graph things that happen at certain times in the day. There's all kinds of different numerical data that we can gather that helps us to make sense of the universe around us. So whenever we draw any type of conclusion just based on limited observations, that can be very risky. If I were to say that all students at the University of Akron are exactly like you guys based on my observations of what happens in this class, I probably couldn't make any kind of accurate description of what exactly students are like here at the University of Akron, because we are not indicative of any of the different majors that happen here, of some of the honors classes that happen here, of engineering classes, or of the arts classes. There's all kinds of different classes that take place here on our campus, and just because we have certain students in one class doesn't mean that that means something about all students in general. That would also be true if I said all students here at the University of Akron are not exactly like all students in colleges around the nation. There are, of course, going to be different places. There are going to be some different colleges like Harvard or Stanford, and then there are going to be other colleges like community colleges. Drawing conclusions based on our limited understanding of what is actually happening can be risky. And so that's why in statistics we try to gather enough numbers that we can measure things to a greater degree of detail. When we look at things like in the picture that's right here, if we were to just say, based on what I see in this picture, all women are taller than men. We couldn't say that because this isn't a good example or a good representative sample of men versus women. And so it can be kind of risky to make those kinds of general conclusions. If we were to measure a large population of people, however, we could probably make some general conclusions about how average humans come out as far as height goes. So when we look at the picture, the graph that's down below the picture of Tom and Katie, you can see that the average female is 5'4", and what that plus or minus 3 means is that plus or minus 3 inches, so from 5'4" up to 5'7" and down to 5'1", that's going to be what the largest population of females are going to be. So if we were to go out and we were to ask around here in this auditorium, how tall are you as a female? Most people are going to be somewhere between 5'1" and 5'7". There may be people that are taller, there may be people that are shorter, but on average, that's what it's found to be as far as females go. Then the average male looks like 5'9", and then 0.5. Plus or minus 3. So most males, therefore, are going to be a lot taller than females. You can see that there's some sort of overlap there. So we have to be careful in how we read graphs and how we look at numbers. And statistics, as we said, is usually a pretty good way to measure things. When we are making wise decisions about concrete things, this is another good example. If we were to ask a question, something that is testable, does having access to a textbook help a student to perform better in a biology class? So if we were to ask that question about textbooks, if you have the textbook, are you going to perform better in this class? We could absolutely test that. We could look at all of the students in here, look at your final biology score, and then look back at whether or not you bought the textbook or not. And so what has been found by looking at large populations of students is that students who have access to a textbook score an average of 81% plus or minus 8% on their exams, while those who do not score an average of 76% plus or minus 7%. So that is going to mean that if you have access to a textbook, it seems like you are most likely going to do better on your exams than someone who does not have access. But there is a little bit of a degree of overlap. So does this explain every situation? It doesn't explain every situation, but it does explain a lot of them. So here we can see this graphed out. This is kind of fuzzy. Is it fuzzy back there? Can you guys see okay? Okay, cool. So here you can see on average exam scores, we've got students without textbooks versus students with textbooks. So statistics can help us in quantifying and summarizing large amounts of information, making it possible for us to draw accurate conclusions. So if we see average exam scores and we see the proportion of students in the population, that most of the students who have a textbook are going to do better than the students who do not have access to a textbook. So just as we can understand that about students, it can also help to tell you something. If you have access to a textbook, you are most likely going to do better in this course than if you don't have access to a textbook. So statistics can help us to identify relationships or the lack of relationships between variables. Sometimes we think things are related to one another, and they are not necessarily. A positive correlation means that when one variable increases, so does the other. So an example might be if we look at crickets that are chirping, we may find that as the temperature outside goes up, cricket chirping is going to go up also. So a positive correlation means that as one goes up, the other is going to go up also. And I don't want to speed through this. I know that I end up talking really fast, and I can still see you all writing. So a positive correlation, when one thing goes up, the other thing goes up also. One of the things that we often heard said and that we often don't understand is that correlation is not causation. Just because two things are related to each other doesn't necessarily mean that one thing is caused by the other thing. In the cases of the cricket chirping, we can find that when the temperature outside goes up, the amount of cricket chirping also goes up. One thing is caused by the other thing. Sometimes we find, however, that things are not related to each other at all. And the famous example of this is that a researcher found that as the temperatures went up during the summer, that the murder rate in the United States also went up. And he also found that the ice cream sales at the local grocery store would also go up. So he made this inference that the number of murders are positively correlated to the amount of ice cream that's being sold. And so everybody kind of laughs at that because it doesn't seem like it makes any sense. What they eventually found was that as the temperatures went up, more and more people would be outside and they would be out going around in their neighborhoods, and that the murder rate would go up because there were more people outside of their houses. During the winter, everybody kind of hunkers down inside of their house because they're so cold and they don't want to go outside. So two things, just because they are both going up, doesn't necessarily mean that one is caused by the other thing. So we have to really watch out for that. Two of the other things that we often talk about in science is pseudoscience and misleading anecdotal evidence. So as we are going out and as we're searching for the truth about this world that we're living in, there are two things that can often get in the way. One of those is pseudoscience, or something that sounds scientific but isn't actually scientific, and anecdotal evidence, which means evidence that's based on your own experience but not on data about the population as a whole. So how to prevent being taken in or fooled by false claims. In identifying these two types of scientific evidence that are frequently cited in popular media. So lots of magazines run ads based on pseudoscience, and lots of times we hear that things are related because one person's personal relationship to that experience, they think that that's related, but what we find out is that they are actually not related. So in pseudoscience, like I said, making some kind of claim about something that sounds really scientific, but it's not exactly scientific. Like we had talked about the case of Airborne. Airborne being that that drink that you could make that was supposed to help you to not get the flu, and it was developed by a school teacher, and it had all of those vitamins and minerals in it, and it was supposed to make it so that you wouldn't get sick. And it sounded like it was being presented as there was scientific evidence behind it, that you wouldn't get sick if you drank this concoction. And it said research studies, that they had done clinical evidence, and it turned out that they hadn't actually done any of those things. And then anecdotal evidence would be like if I said, whenever my kid eats Snickers candy bars, I notice that he doesn't get sick in school. So you should feed your kids Snickers candy bar because that'll help your kids not get sick in school. Based on my own experience, that might be true. It's not true, not in my experience. But sometimes people say, I think these two things are related because I have seen this happening. And they are not always linked to each other. So here is an example of pseudoscience. We've all gone to the grocery store. We've seen these claims about organic foods. And yes? I'm sorry. You want me to go back one? Okay. Okay. Thank you for telling me. I don't realize that I talk that fast. Sorry. Sorry. And I will post these all up after I talk, so that if you want to get them off of Springboard, you should be able to get them off of Springboard. All right, take a couple more seconds, and I will move on. Sure.
Will the lab quizzes be included in our exam?
No. The way that works is that there are lab quizzes in the lab, and your lab is worth 25% of the overall grade for this course. So your lab quizzes will add up to, I think it's 100 points, and there's 2 of the lab quizzes that'll be thrown out, so they'll drop the lowest 2. And so it's not going to be added to your exams in here, but the grades all come together as the number of points. Okay. All right. Anybody else before I move on? Okay. So we've all gone to the grocery store and we've seen claims like this made, where we see organic foods, and then they have something that looks like this, where it says it's a pure food, there's no genetically engineered ingredients, it's wholesome corn, organically grown, stone ground, cooked, packed the same day. So it sounds like something that's going to be healthy for us. It sounds like it's going to be a food that's better for us than if you go get a bag of Cheetos. It sounds like the difference between those is night and day. But this type of food is still fattening. It's still cooked in oils. So it is not a fat-free food. It doesn't have hydrogenated oils, but it does have oil in it. And corn is still a carbohydrate, whether the corn is in a Cheeto or the corn is in your bread or the corn is in your cereal. It's still going to be corn, which still has calories in it. So when you're looking at your choices of food in the grocery store, you may look to pick the foods that sound healthier. They say they don't have any calories, or it's a fat-free food, or that it's got high in protein or lots of vitamins and minerals. And what you may find is they're just putting these things on there that are naturally happening anyways. Foods have vitamins and minerals in them anyways. There are a lot of foods out there that are fat-free that are not sugar-free, so they still have lots of calories in them. Just because you see these things written on the food packaging doesn't necessarily mean that you're going to be healthy and fit when you eat them. They're still chips. And so pseudoscience is whenever we represent a claim to sound scientific, organic sounds scientific, but it's not necessarily so. And if you may have heard of this one from the TV commercials when you were a kid, where they had the gum and they said 4 out of 5 dentist surveys recommend sugarless gum for their patients who chew gum. So what this kind of makes you imagine is that if you went to your trusted dentist and you said, what kind of gum should I chew, my favorite dentist? Should I chew gum that has sugar in it, or should I chew gum that is sugarless? Well, most likely he's going to say to you, chew sugarless gum, because that's what everybody says, that sugar is not as good for you as sugar-free. But how do we know what they know here? How do we know what kind of experiment that they went through, or what kind of survey procedures that they went through in order to gather this data? By just making a claim like this, by saying, well, 4 out of 5 dentists would recommend that you choose sugarless gum if you're going to chew gum. Well, that sounds good, but what kind of experiment did they do? If they're not willing to tell you what they did to come to those conclusions, then it's often not going to be a very good conclusion. You may also find that the statement may be factually true, but the general relationship implies that it may not be. What if we only went out to 5 dentists here in Akron, Ohio, and we only asked 5 dentists? It would be different if we asked 1 million dentists across the entire country, but if we only asked 5 dentists, that may not be a representative sample. So you have to be very careful when you're looking at things like pseudoscience or things that sound scientific, because how do you actually know that's true, and how do you know it's not a marketing technique? So I went and I Googled what are some examples of pseudoscience. And when I looked at the Wikipedia page for it, it was really interesting to see some examples of pseudoscience. Things that sound scientific, like astrology. If you hear, well, the Venus is in this orbit on this day of the month, and then Mars is up here, and the Earth is here compared to the Sun is over here. It sounds like maybe they've figured out some kind of scientific way to tell you what's going to happen during the month if you were born in that certain month. But astrology has proven to have no factual science behind it. Sounds scientific, and a lot of people rely on this, so they will draw these conclusions about this. But astrology is not actually science. And I remember I used to teach high school, and one of the guidance counselors was getting kids to sign up for their science course, and they said, oh, you should take astronomy. It's where you get to learn about your horoscope and stuff. And I thought, oh, no, this person is a guidance counselor and they don't know the difference between astronomy and astrology. Astronomy is the legitimate scientific study of the stars, and astronomy is making predictions based on where the stars are. Another thing that's found to have no scientific backing behind it is extrasensory perception, or ESP. If you've ever heard that some people can tell things with their mind, and you see these stories on TV where somebody's sitting behind a partition and they're saying what's on the card, like circle, square, wavy lines, and they seem to be able to figure it out. They have not ever actually come up with any link between a person being able to read minds and actual science. So we may find out at some point that there is a legitimate explanation for those things, but we haven't found one so far. So that's why we would call it pseudoscience. A lot of you probably watch those ghost shows on TLC where they go out with the counter and it shows electromagnetic fields and where ghosts should be. And some of you may have even thought that you felt ghosts in a certain place, or have gone out to test for ghosts. There is no test for ghosts at this point. Nothing that is actual science that links those things together. Could we find a way of actually finding ghosts at some point? Sure, but we haven't found that yet. So people are going to keep looking, and they're going to keep trying things, and that's what's kind of cool about the quest for knowledge. How do we know what's going to be true? Well, we try and figure out some way that we can scientifically measure it. Faith healing is another one of those things where you see a preacher on TV hit somebody on the forehead and they fall down and believe that they've been healed. There are some reasons that people think that they can be healed in faith healer type of situations, but there's never been any scientific backing behind that. Creation science is an interesting one, about like the biblical flood and the story of Genesis and things from the Bible. The Bible has never been shown to be a scientific document. It's a religious document. And so could we find at some point that everything was created the way that it was explained? Sure, we could find that out. But as of now, the best explanation that we have is the fossil record and the DNA record, and going out and looking for fossils and looking for the remains of animals in ice and different things like that. One of the most interesting ones that I put on here, because I think that it's really kind of poking at our imagination, was scientific racism. It used to be that scientists thought that they could measure a person's skull, and that the size of their skull would tell how intelligent they were, or that there were certain races that were superior to other races, and they thought that they had this all scientifically figured out, that they could explain that one race was superior to another one. And that's been the cause of a lot of racism over the course of the years. And so it's something that's really interesting to look at, because what we found is that humans have a variability of intelligence, no matter whether you're looking at someone who's Caucasian, someone who's Asian, someone who's African American. We found that there's a wide variability, and a lot of intelligence has to do with how children are raised and a lot of the behaviors that they're raised around. So no human is scientifically better than one or the other one. It may all have to do with culture and the way that we're raised. So if you want to look more at that, Google the Wikipedia page. It's definitely fascinating to see how some people think that science explains one thing when it doesn't actually explain that. So you don't have to write this down. I'm just going to explain to you what it is, because a lot of times when you hear anecdotal evidence, you think that you're not really sure what that means. You may have just heard based on stories. So when I Googled anecdotal evidence, what it said was that We were looking at evidence from anecdotes, which is basically somebody says that there's a correlation between two things, and that there isn't exactly a correlation there. So if a small sample of people believe that something is good for children, like let's say me and 5 of my mommy friends get together and we all decide that our kids are better than normal kids because we feed them all Snickers. If we say that, then we may be able to convince some people because maybe all of our children are on the honor roll, or maybe it's just that we're 5 people and we have had our kids and pushed our kids really hard and they've gotten on the honor roll and Snickers had nothing to do with it. In science, what we find is a lot of times when people make these outrageous claims that they've cherry-picked who they want to be represented by the sample, and so it's really what's called a non-representative sample. If me and 5 of my mommy friends who also work at the University of Akron, and we're all professors at the University of Akron, and we have kids on the honor roll, maybe that's the correlation rather than the Snickers bars. Maybe the fact that they all have parents that are professors is the reason that they're smart. So in order to do any type of science, usually the larger the sample size, the better that it is. Because that helps to weed out the claims by the, I don't want to say the crazy mommies, but the mommy groups that claim that something is better for your kids, or the groups that claim that they've found these weird health things. And it's just better to be able to support things with science than to not support it with science. So one of the big ones that's in the news right now is the vaccines thing. You may have heard, you go to the pediatrician and the pediatrician wants to vaccinate your children. In order to get them enrolled in school, you have to take vaccinations. If you're any of us right here, you may have heard that you should get a flu vaccination so that you don't get the flu during flu season. A lot of times when somebody has studied something, they so badly want to believe that what they think is true that they cherry pick their population in order to get the results that they want. So what had actually happened with the story on vaccines is that there was a scientist, a pediatrician out of England who found, he said that he found, a link between vaccines and autism. So you've probably all heard that if you give your kid vaccines, that they run the risk or a higher risk of getting autism. And so what this scientist actually did was that he found 6 children that had autism, and he found that at the time they were diagnosed with autism, they had all been given their vaccines. So he published in a legitimate journal that children who were given vaccines had a higher rate of getting autism. So everybody, went kind of wild with this. They said, we don't want our kids to get autism. We're not going to give them these vaccinations. And what they found when they did a bigger study, a scientific study involving hundreds of thousands and millions of children, is that children who are going to develop autism will often develop autism at about the age of 2 years old. And so about the age of 2 years old is when we tend to give a lot of vaccinations to our children. And so there was no statistical correlation between children who had gotten vaccinated and children who developed autism. And that was shown in millions of children. So this doctor who had made these outrageous claims was actually stripped of his medical license. He had to retract his article from this very scientific journal. But we still hear this today. We still hear on the internet that people think that autism and vaccinations are correlated to one another. And that's actually something that's very dangerous. What we need to do is, in order to back up those types of claims, we should do real scientific studies. And in this case, the scientific study proved that that was not true. So there are actually limits to what science can do. Scientific questions need to be answered in a certain way, and there are certain questions that science cannot answer. So there is the scientific way of understanding the world around us by going out and collecting evidence, or collecting, like in the case of what were things like 65 million years ago, we can find dinosaur bones that show what things were like 65 million years ago. If we're trying to look at something about the human genome, we can collect DNA from hundreds of thousands of humans or millions of humans. If we are going to ask a scientific type of question, we need to be able to collect evidence, and it needs to be empirical. So empirical basically means that it's testable. We can show that one thing is true or that one thing is not true. Some things that we can't answer when we're looking at scientific types of question is questions of values or questions of subjectivity. Science can't prove what my opinion is about any certain type of topic. It can't prove that. It can't prove anything about any type of religion. Religion is something that's based on personal opinions, based on values, based on scriptures, based on different things that science cannot prove. Science also can't prove things that are questions of morality. If we say, is that right or wrong? Scientists can't answer that using science. We can have opinions about whether things are moral or whether things are immoral, but those things aren't questions that would be answered by science. If I said, my computer is really amazing, that is my opinion about my computer. That is not a type of question that science can answer because that is an opinion. So there's going to be certain types of knowledge that we can go out and search for that's based on opinion, based on subjectivity, based on values, based on morals, and those are going to be things that cannot be answered using science. So we get to the end of chapter 1. That's kind of the end of scientific thinking and the way scientists go about explaining the world around them. What we're going to be moving on to now is chapter 2. We're going to be talking a little bit about, and you don't have to write this down, this is going to be what you're going to see coming up in this chapter. You will see what atoms are, their structure, and how they bond together. We will be looking at and talking a lot about water and why it's necessary for life. We're going to look at carbohydrates. We will also look at lipids and proteins and nucleic acids, which are the building blocks of life. And we will understand their structure and their function. So as you are reading in your book, which I hope that you are all doing, we have finished chapter 1, so if you have read it, it's already behind you. You can move on to chapter 2. If you haven't read it, you should start doing that at this time, because we're going to move through chapter 2, and you're going to want to read that chapter also. In order to get a good understanding of these things for the test that will come up, yes, you should focus on the things that I talk about in class, but you should also be reading along in your textbook to make sure that you understand that. Is there any questions at this point, or I hear general murmuring? Yes?
Did you ever find out, figure out which date was Deep Pan?
I did not. I do need to look at that. Will somebody email me and ask me that? If I don't write it down, I don't remember what's going on around me. So what we're going to begin talking about in this section is atoms forming the molecules through bonding. And when we think of atoms, usually the first kind of picture that comes to our mind is this nucleus with these electrons all traveling around it. And this is actually not an accurate photograph. It's not even a photograph, it's a drawing. That's not exactly an accurate representation of atoms. Starting off with first, what are atoms? An element is a substance that cannot be broken down chemically into any other substance. So if you remember your periodic table from high school chemistry, or if you've ever seen a periodic table, you can probably think of some general things that are on the periodic table. You can think of things like gold and things like copper, things like silver, titanium. Then you can probably think of gases like neon or argon or radon. You can probably think of the things that are in the air around us, like oxygen and nitrogen and carbon. So elements are going to be things that are going to be made up of only one type of atom, and they are not able to be broken down any further by a chemical means. And so then looking at what are the parts of these elements, they are atoms. Atoms are a bit of matter that cannot be subdivided any further without losing its essential properties. So atoms are going to be these building blocks. If they're all the same, they make up atoms. If they're different, they make up molecules. And we'll be looking at different types and how they work to structure life here in just a minute. I see that you're writing, so I'm going to take a drink. Okay, so I'll post these up. You'll be able to go back and look at them if you missed anything. So when you're looking at the basic structure of an atom, atoms are going to be made up of the nucleus, the protons, and the neutrons, and then it will have electrons around it. So in looking at this picture up here, we've got our hydrogen atom. Inside of the nucleus of a hydrogen atom, you've got 1 proton and you've got 0 neutrons. And a hydrogen atom has 1 electron that's swirling all around it. It's not going in a straight path, however. It's kind of surrounding it like a cloud. It's never got any one fixed position. So when you're thinking of an atom, you should be thinking kind of this cloud of electron energy around this dense core. If we look at a carbon atom, here we have the nucleus of the carbon atom. It's got 6 protons, so you can see the little plus signs here and there. You've got 6 neutrons, which are the other ones, which are neutral. And you've got your 6 electrons that are found in this electron cloud that's surrounding this atom. And the reason that they are put together in that fashion is that we have forces of attraction between the positive and the negative charges. So the nucleus here of the atom is going to always be positively charged, and then the electrons that are surrounding it in this cloud are going to be negatively charged. The middle part, the nucleus, is going to be where all of the weight of the atom comes from because the electrons are almost of a completely negligible weight. So down here you can see protons, neutrons, and then electrons are represented as much, much smaller. So the electrons are negative and they're floating around this positively charged core. And so when we are looking at these electrons, that's the same one, I think. Okay, so as we're looking at our periodic table is going to be able to tell us some certain things about the atoms and about how they're put together. So if you see a periodic table, it's usually going to have boxes like this that have the elements symbol in the middle. This one would be for oxygen. And it tells you the element's name. It tells you the element's number here in one of the upper corners, and that's going to be a whole number with no decimal after it. And the atomic number is the number of protons that are found in the atom's nucleus. So this is going to be the number of protons. And then you'll see a second number that's down here that's called the atomic mass. And the atomic mass is almost always got this decimal after it, and it's the combined mass of the atom's protons and neutrons. So the atomic mass is what the entire nucleus of this atom is going to weigh. But the atomic number is going to be the place that it's found on the periodic table. We've got our symbol for what it is there in the middle, and if you look at your periodic table of elements, you can find all of these different types of elements displayed in order on the periodic table. In the book that you guys have, there's going to be a certain element color code. You can see that these are kind of the big 10 of the elements that we'll talk about over and over again as we move throughout this book. Hydrogen, carbon, nitrogen, oxygen, sodium, phosphorus, sulfur, chlorine, potassium, and calcium. Now, the two that students often have the biggest trouble with is going to be sodium, because it's not S, it is Na. Sulfur is the one that is S, and K for potassium. So just because they don't exactly make sense the way that they're set up, but we will be talking about these as we move through the book. And so whenever we're talking about elements, we have to also talk about what's called an isotope of those elements. So sometimes we find that atoms have the same atomic number, which means the same number of protons, but they may have a different atomic mass. So often when we talk about the building blocks of life, we're talking about carbon-12. So carbon-12 is very simply 6 protons, 6 neutrons, and 6 electrons for an atomic mass of 12. But sometimes when we're talking about how carbon breaks down over time, we may actually end up with carbon-13 or carbon-14. So if we see these different isotopes, they'll have a different number after them that means that it is an isotope. So the difference between that is that in carbon-13, you can see that we have 7 neutrons instead of 6, and we have here in carbon-14, we have 8 neutrons instead of 6. And so what isotopes tell us is basically how things are breaking down over time. Certain types of elements are going to have a number of years or sometimes even a number of minutes of half-life. So that means the amount of time it takes for certain types of substances to decay. And so it's important for us to be able to understand these things in terms of how they're going to react with other things that we'll see on the periodic table. Sometimes we'll hear of different types of atoms that are going to be radioactive. What that means is that in the atomic nuclei, they are not stable, and so they are breaking down spontaneously. Usually when we think of things that are radioactive, we think of things like nuclear generators, or we think about the nuclear accident at Fukushima, the Japanese power plant, or we think of like 3 Mile Island or Chernobyl. When something is radioactive, that means it doesn't have a stable nuclei, and it's breaking down spontaneously. In the case of those nuclear reactors, it's releasing so much energy that we're able to draw power from those. So those atoms are considered radioactive, and they're always releasing energy at this constant rate, and they are tiny and very high speed, and they're carrying lots of energy. So if something is radioactive, it has a lot of energy to it. And so those things play a certain role in our environment, like uranium is an example of an element that's often radioactive. So as it's releasing that radioactivity, it's releasing lots of energy. As we go through this course, we're often going to find that there are 25 elements that are found not just in your body, but in everything that's alive, basically in all of those bodies. And in humans, there are 4 that are the big ones. Your body is mostly composed of oxygen. You are about 65% oxygen atoms. And you are about 18.5% carbon. You are 9.5% hydrogen, and you are 3% nitrogen. So of those 4 elements, those things compose of 96% of your body. So you are mostly made of carbon, oxygen, hydrogen, and nitrogen. And then the other ones that make up the other 4% of your body are going to be things like calcium, phosphorus, potassium, sulfur, sodium, and chlorine. And these are going to be the basic building blocks of the things that we eat, that we will find them as vitamins or as minerals. And we find trace amounts, which is about 0.1% of 15 other elements that are found in your body. So if you want to look at those a little bit further, you should look at them inside of your book. But know the big 4. Know that oxygen, carbon, hydrogen, and nitrogen are the big 4 that make up almost all of your body. So as we're looking at these things both within our body and in the environment around us, what we are going to find is the reason that they are able to react with one another is because of their electron shells. So just as we have this nucleus here that's in the center of each one of these atoms, we also find that they have electrons that are swirling around in this cloud around them. And in that cloud, they will either have an amount of electrons that will make them stable, or they'll have an amount of electrons that they either need to share electrons with another element, or that they're going to take one from another element, or they're going to donate one to another element. And so we'll talk about all the different ways that those different types of bonding occurs. So in this first one that we're looking at right here, this is an oxygen atom. Here we have the nucleus of the atom, and here, if we count around in the shell of electrons around it, we can see that we have 1, 2 in the first shell. So in the shell that is closest to the nucleus, we have 2 electrons. And then in the outer shell that defines how this atom is going to react in the environment, we can see that we have 1, 2, 3, and then 4, 5, 6. So oxygen has an atomic number of 8. That means it has 8 electrons. But as you can see from this and this right here, there is a vacancy where oxygen, in order to become stable, needs to get 2 more electrons in order to fill that outer ring. And so it's going to get those 2 electrons from somewhere, and that's from another atom that's willing to give up those electrons or share those electrons. So when you hear about the oxygen that you breathe that's all around you, you aren't just breathing in oxygen as O with just oxygen. You are breathing in O2. Oxygen is O2, which is a gas, which means that it's 2 atoms of electron, 2 atoms of oxygen that are bonding together in order to share these vacant spots here in the outer shell. So we would call this, in nature, an unstable atom. Here you can see hydrogen is another example of one of those unstable atoms, because hydrogen has that 1 electron in its outer shell. Now it's only got 1 shell, or 1 ring around it. And so since it has this other vacant spot, it's going to be highly reactive. Hydrogen reacts with a lot of other atoms that are around it. If we look at helium, however, helium exists very stably as a gas. It's got 2 electrons in its outer shell, and since it has no vacancy like this one, it doesn't react with anything else. So helium is a stable atom. Here you can see a nitrogen atom. It's got its 2 electrons here in the inner shell, and it's got 1, 2, 3, 4, 5. So that means it's got 1, 2, 3 vacant spots. So only when atoms have electron vacancies is their outermost shell able to interact with other types of atoms. So if it's like helium, or here if we see neon, we can see that those are stable because they don't have any place to get other electrons. And then these guys over here, hydrogen and nitrogen, those are going to be ones that are not stable because they're out basically looking around to find those other elements. So one of the reasons that carbon is so versatile is that it is so symmetrical. If you look at it, it's got that inner shell filled with 1 and 2, and then it's got this second layer here on the outside, its second electron shell, that has a capacity of 8 electrons, but it has 4 vacancies. So if you look at it, it's got 1, 2, 3, 4 electrons, and it's got 1, 2, 3, 4 vacancies. And so carbon is going to be very reactive. It's going to build these very long chains. You're going to see it in your carbohydrates, in your proteins, in your sugars. You will see it as this building block molecule in a lot of the different molecules that we'll talk about. And so carbon is really necessary for life. Every one of us is called a carbon-based life form. That's one of the ways we determine if things here on Earth are alive or not, is that they have carbon as this building block of their structure. And that's also one of the ways that as we go out and explore the universe, that we know that we haven't found anything that's alive in the universe yet, because we haven't found anything else that's made of carbon the way we and all living things here on Earth are made up of carbon. At some point, if we find something alive out there somewhere in the universe, it will either be a carbon-based life form, or it will not be made of carbon, and it will be alive some other way, and that will be a miraculous moment when and if we find that thing. So, in talking about our atoms a little bit more and talking about their charges, ions are these charged type of atoms. So we can see here we have Na, which is sodium. We have Cl, which is chloride. In Na, or sodium, we have 11 protons that are there in the nucleus. We have 11 neutrons. And then we have 10 electrons that are in this outer shell. In chloride, we see that we have 17 protons, we have 17 neutrons, and it has 18 electrons. So in order to go from sodium having 11 electrons and chloride having 17, sometimes in ions, or all the time in ions, we see them donating electrons to other atoms. And that's how we see things like charges. If you've ever seen a battery has a positive side and a negative side. We see that things are often attracted to each other in nature, thinking about like magnets and things like that. But atoms are attracted to each other also because this chlorine is taking one of the electrons from sodium, and so they will be bonded together and they will make NaCl, which is a molecule of salt. And salt is very important to life that's around us. If you think of like seawater and a lot of things that are alive in the sea, but you have to have a certain amount of salt in order to be alive at all. And so when we talk then about the bonding, looking at atoms that are bonding together to form molecules and compounds. Yes, ma'am. Can I certainly can. Okay, take a couple more seconds to finish up whatever you're writing there. Okay. So going from charged atoms then to atoms are bonding together in order to form molecules and compounds. And so these are the building blocks of life and everything that's all around us. So these atoms come together, bond together to form molecules or compounds. And we're going to talk about 3 different types of bonds, which I don't know that we'll get through all of them today, but I'll get as far as I can go. So when you're looking at atoms, obviously we aren't looking at actual pictures of real atoms. Sometimes in high school you may have learned to do these, what's called a Lewis model, where it looks like these little sticks and everything is all put together. Sometimes you actually use the ball and stick model or the space filling model. What we'll be doing as we're moving through this will look most like this one that's here on the end. But just in case you're wondering, is that the same thing that I was talking about in high school whenever you took high school chemistry? Yes, this is the same thing. The first type of bonds that we'll talk about are called covalent bonds. And if you want to know the one big way to understand covalent bonds is that covalent bonds share electrons. So, right, covalent bonds, and they are sharing electrons. So what you see here in this first picture up here is that we have 2 hydrogen atoms, and each one of those hydrogen atoms has 1 electron in its outer shell. So here you see the nucleus of this hydrogen, the nucleus of this hydrogen. Each one has 1 electron here in its outer shell, and it also has 1 vacant spot here that it can get an electron from somewhere else. So what happens is that the nuclei of these 2 hydrogen atoms are going to come together, and they're going to share 2 electrons. And so the electron from this one up here and the electron from this one over here are going to be shared between the 2 of them. It kind of looks like a figure 8 if you look at this spinning around these 2 nuclei right here. And so it's going to circle around both of them. And when they come together, they are going to be H2 or a hydrogen molecule because you have 2 of them together. And so that is what's going to make them stable, and then that's what's going to make them exist in our environment. And so we see that like what I talked about with oxygen gas around you in the atmosphere. These two pairs of electrons are going to be shared between oxygen atoms to make an oxygen molecule, and they are going to share these 4 electrons. What? Oh, sorry. And then here we see another one. We've got carbon, and it's sharing these electrons with these hydrogens that are all around it. So this would be called a CH4 molecule. That's methane, and that's highly combustible. So I don't see you writing. I'm going to move on to the next one. We also have a type of bond where rather than sharing like covalent bonds, sometimes atoms are going to give up or they're going to accept electrons. So what we see in this case that we talked about with sodium and chloride, we've got sodium that has an electron that it can donate, and chloride ion that has a place for an electron in order to accept it. And so because they have opposite charges, sodium is going to be positively charged and chloride is going to be negatively charged. When they come together, one will donate, the other one will accept, and you'll see a NaCl compound. So they are going to go through a donation and accepting type of situation. So often, these are the types of substances that we're going to see crystals form in. So because of the way Na and Cl come together, they're going to actually form these crystals. And you can probably think of some crystals of other things that you can see, like sugar crystals. So we've got Na plus and Cl minus. attracted to each other in order to make this compound. And so this is where I'm gonna end for today, and we will do the same thing that we did the last time, where I'll post those videos on YouTube and on Springboard, and then you'll take notes on each one of the videos. So we will not meet in here on Thursday, and I will see you guys next Tuesday in this room. Yes.
Changing the lab class.
Yes.
I did.
Okay.
But then they canceled that Thursday lab. So that would technically still put me behind the lab, right?
They canceled that Thursday lab.
Yeah,
you mean?
last Thursday they canceled the lab. A power outage happened.
Oh, yeah. I had forgotten about
I
that.
actually got a chance to get into the Tuesday class.
Okay, yes, you would be one lab behind, so you need to check on Springboard and look at the syllabus, and then when we come in, it would be tonight, right?
Yeah. But
no,
it says
it's
from
not.
The 3 to the 7th, we're not having labs.
Yes, we don't have any labs this week.
So I don't know
That's
if there's
right.
a chance I can go make it up tonight, or
There are no labs at all. They're not even
So they're
meeting.
not even open.
Yeah.
Okay.
So you would come in next Tuesday and
Okay, and
do
then
that.
would I just go to the next Thursday lab too to make up lab class, or?
Oh no, it'll just be like you
I'll be
would
able
drop
to-
that
I'll be
one.
able to-
It won't affect your grade at all.
Okay.
Just make sure that that you know everything that your teaching assistant's telling you, that you look
Okay.
through the syllabus because they just went through
And
the
then
syllabus.
If there's another makeup session where I can make it up through that class, I'll be able to make it up through them. From
There's
the last lab or
there's no
anything like that?
makeups for the labs, but that's why they dropped the lowest lab scores. So that won't affect your grade at all. Because they know that that's going to happen, and there's no way to make them up because we can only have those 40 students in labs at a time, and because we have to order supplies and stuff like that. So we don't set up
Okay.
for 2 different labs.
So we're good.
Yeah, you're good. You are good. Don't worry about it.
All right, thanks.
Yes, ma'am. Always going to go around and collect those.
Okay.
Thank you for bringing them to me. That was very nice of you. Thank you. Thanks.
Is it okay to use the first edition of the book? Is it really that big of a difference?
It's not exactly the same, and I'll definitely be lecturing out of the second one, and the examples will be from the second book. But you can kind of compare those two. If you like Google the difference between the books, you can find out what the differences are.
Okay, cool.
I can't tell you you can.
Okay.
I can't tell you you can't.
Okay.
I have the athlete form for you. I don't know if you've seen this.
I have not. What is this?
It basically just says like I'm gonna be gone these days.
Oh,
I'm
okay.
Not gonna miss anything. Like just basically review. I wrote the syllabus. But I just need to like sign it to make sure that
That you told me.
3 days.
Okay. You have a pen? I don't have a pen.
I do.
Here, she's actually got her pen handy.
And if I have to miss 3 lab days too.
That will affect you a little bit more. You need to talk to your teaching assistant and make sure that you get those quizzes and that you read through the section of the lab. If you miss 3 labs, technically 3 labs will not affect your grade at all. But don't miss those 3 lab quizzes because you can still take them in the computer-based testing center.
Okay, cool. And this is for you.
Oh, thank you. All right. Thanks.
Thursday with the power outage was out, so I didn't get to do that.
Yes. That one lab, because it was canceled on Thursday, I think they're going to redo it later on in the semester, but I don't know when that's going to happen.
And for the homework, I couldn't log on to Springboard, but I figured out what the problem was.
Okay, so
But would that
if you
have to
miss
affect-
one, it's not going to affect your grade at all. I'll drop 1, so if somebody else misses 1 later on, that it's okay, and that won't affect you at all.
All right, thank
So that's
you.
good. All right. What?
You shouldn't like redo it, like turn it, still do it, put it in the Dropbox.
Oh no, I closed that Dropbox, so that one will be dropped for you. No, don't worry about it, and then we'll just keep going from here. Yeah, yeah. Okay. Thank you. Awesome. Thanks.
I had a question. I'm Bethany. I'm the one who emailed you about the document not opening up in my Word. I have
Oh, okay.
the newest version of Word, so I don't know why it wasn't working.
Okay.
Are the directions going to be the same?
Yeah, they'll pretty much be the same.
Okay.
I haven't figured out anything different that we're going to do. You can call the the help desk here.
Okay.
6888 is the extension,
Okay.
and a lot of times they can walk you through whatever's the problem with
Okay.
your Word,
Okay.
even if it's on your personal laptop.
Yeah, I don't know what. My laptop is weird. I'm
Hey,
still trying to figure it
technology
out.
is such a pain in the butt sometimes.
It is.
It's like it
I got
works or it doesn't
4
work.
months ago, like my laptop, everything is new, so I don't know why.
So you're
wasn't
like, it
working.
should work.
Yeah.
I know. I totally get it.
It's okay.
Yeah, I know.
Do we have lab Thursday?
This Thursday, no, there's no lab this week because of the Labor Day holiday. So whenever we have one of those weeks, we don't have lab at all. We don't have lab at all the week of Thanksgiving either.
I don't know if you can like double check to make sure that you got my paper.
I can.
Because like I have pages for my Mac, and sometimes it won't open on certain
Oh,
computers.
okay. Were you
so-
the one that sent me those TXT files? I wonder if that was you.
No idea.
Will you email me so I can look at it when I'm
Yeah,
in
yeah.
front of my computer, and
sure,
I will
yeah.
send it back.
And then I had like a couple other questions, but I'll email
Oh.
you about those ones.
Yeah, a lot of times when I'm sitting down and I'm writing, I can remember to answer
Okay.
them all.
Okay.
Unless it's something you want me to answer now.
No, I'll email you.
Okay, great. All right,
Great.
thank you. Hello.
Hello. I missed class Tuesday, and I
Okay.
printed out the syllabus, and I asked someone, and they said that you didn't collect it.
I don't know.
Okay. All right, I just wanted to make sure.
Well, that was good of you, yeah.
And and I missed lab on Tuesdays, but there was a quiz in there that we did.
There is a quiz, but the first quiz is actually open. It's in the computer-based testing center. So
Okay.
you can go there and you can still take the quiz if you
Oh,
read
I can.
through. We did lab 3 that week because there was a problem with the termites.
I read about that.
Yeah.
Yeah.
So if you read lab 3, you can
Okay.
still go in and take it up until this next Monday here.
Up until Monday.
Yeah, I usually do the quizzes Monday at noon to the next Monday at noon.
Okay, just in the computer lab.
Yep.
All right, thank you.
Thank you.
We'll see ya.
Sure.
We didn't have an attendance sheet, did we?
We did not. I just have these things that I was asking some questions on. So
Perfect. My name's on that.
good, good, good. Thank you. Thanks.
What was this?
I asked them some questions if they had any questions about the Thursday assignment or anything like that.
Watch the YouTube.
Yeah.
Take notes.
Yeah,
Like,
yeah.
Put your thoughts back.
Yep.
Spit our thoughts back.
Yeah, basically. And I have some over here too, so I'm actually going to go grab them. So what happened with you dropping?
You have to sign this, and I gotta give it back.
You want me to sign it?
Yeah, just like
Okay.
stay trial.
Okay.
No, I said this my conference.
Don't do that. Oh, look, there's none of them on this side. Everybody must have sent them that way.
I grabbed my statistics class. I stretched over 4 subjects.
Well, 4 classes is a big load in college.
Yeah.
So I totally understand that.
So you know me, all the Vyvanse in the world couldn't make me concentrate.
Yeah.
Allegedly.
All right. Let me see what I got here. Okay. Escape.
No, I just started losing my confidence. That's like I looked online, and then I found a class that came in earlier.